Hello dear students, welcome to the 8th session of the JEE Advanced 2023 preparation. We have started organic chemistry learning. In the previous session we had covered some questions from the general organic chemistry, isomerism and electrophilic substitution reactions on benzene, and in this session also we are going to cover some more question based on this, because you found that the question from these topics are very frequently asked and also they have a connect to the upcoming chapters also. So the link between the general organic chemistry with the other chapters or isomerism with the other chapters has to be properly established. That's the reason why most number of questions are discussed from this topic, and these sessions are divided into part 1 and part 2. I'm going to cover the maximum number of questions because these are the important topics of organic chemistry learning, and I also ensured that the question from the IUPAC nomenclature can also be covered, because if you are asked the question from this topic, you should consider yourself as lucky, because those questions are easy, at the same time they consume less time, isn't it? Now you can see the question when the name is given and you have to write the structural formula. If you remember, you have to write the total number of carbons in accordance to the root word. You can see the root word is hex. After that you are going to number it from any side that you wish, doesn't matter from whichever side you write. You can see the main functional group is oic acid, and you know it's a privileged group, so it gets the first position. After that you have to keep filling the substituents. Second has OH, isn't it? Third has ethinyl, you know ethinyl is C triple bond CH. Fourth has methyl, and you can see there is a double bond at third position and there is an ine at fifth position, isn't it? So the option which is matching to this requirement is this one. So option D is the right answer for the question. Easy questions are asked 8 times in JEE, isn't it? Now you can see the other question is, looks to be very simple. This is the IUPAC nomenclature of the aromatic compound, and you know that most of the aromatic compound IUPAC nomenclatures are the common names. So we need to be careful, and this is more than one choice correct answer. And there are two substituents which are given here. One is the chloro, the other one is methyl, isn't it? And when there is a substitution on the benzene, one has to remember that we follow usually the alphabetic order. And you know C comes first in chloro than M of methyl, right? So chloro comes first. You can see chloro comes first in these two options, whereas M comes first in these two options. So right answer for this question is B as well as C. As I told you that common names are the IUPAC names, so there is no controversy in calling that as a toluene, because you know methyl benzene is toluene, right? A more than one choice question. Now let's see the next question from the conformational isomerism, linking it with the optical isomerism. He is asking you to identify the identical molecules, right? You know, for that you have to rearrange the what you call the structures of or the conformers of these PQRS which are given over here, right? So now that I'm going to do initially. So what I'm going to write is I'm going to take up each option's conformational isomer in a different manner. I'm going to rewrite it. First I'm going to write what you call the rewritten Newman projection of all these structures. Alright. Then I'm going to write the Fisher projection, and after that I'm going to write the names of that so that you can identify which are what. You can see that this structure is given. I want to get this Y-shaped structure for the easy identification of the group. So what I will do is I'll rotate this carbon atom. See, this carbon atom I am rotating by 60 degree. So what will happen? CH3, alright, CH3. I am rotating this by 60 degree, isn't it? You can see C2H5 will occupy this position. Do that with all the examples. You can see I am rotating it here. So I get H here. I have to acquire that Y shape, isn't it? You can see that I am doing that with this carbon, right? First one, which is towards myself or yourself. So this is H, shifted it, you got C, CH3, OH, and then CH3, rotated this as well, right? And after that I'm going to do the same with this orange shade. You focus only on that. So what do you get here? OH, isn't it? CS3 and then CS3. Do that with this. Alright. This is the easiest method of doing this question. Alright. You have H here and CS3 here. After that you are going to write the next group as it is, because anyways the orientation of the next group is Y. Alright. You can see that there is an OH here already existing, and there is a CH3 here existing, and there is already a methyl here. Alright, I'm going to do the same here. You have H, hydrogen, and then methyl. Over here, what do you have already? Which group do you have already? C2H5, hydrogen, and C2H5, isn't it? Over here, you already have C2H5, isopropyl, and OH group. So after doing that, I am going to draw the Fischer projection of this particular structure, isn't it? So I am going to draw it. Then I am going to write the name of each compound. Carefully observe what I am exactly doing here. Probably you will get a hint how to solve such type of questions, right? These questions converting Neumann to Fischer, Fischer to Sohars are frequently seen in the exams, isn't it? So you should know the technique how to do that. You can see that this carbon I am writing here, this blue one. Okay, so what do you have here? You can see that it has C2H5 and CS3 eclipsing with each other, isn't it? So these two groups always eclipse. What do you have then? You have this carbon CH3, and this side you have another CH3. You can see CH3 and OH are eclipsing. Over here two CH3s are eclipsing. You got it, isn't it? Now you can see over here what I am going to write. You have, I am writing this carbon over here, isn't it? So you can see it has CH3, alright, and this has C2H5 over here, the backside one. This has OH, C2H5, alright, isn't it? So this has CH3, upside carbon I am writing CH3, and hydrogen is eclipsing with it. Alright, hope you understood. I am writing this carbon over here. So you have C2H5, CH3 eclipsing, you have the hydrogen here, alright, and you have this group. Okay, so you can see two hydrogens are eclipsing, and this group is eclipsing also with the hydrogen, isn't it? Now look at this. I am writing this carbon over here. You have hydrogen and OH on the top. You have hydrogen here eclipsing with C2H5 here. You can see these two groups, and you can also see that there is a CH3 of this carbon eclipsing with the isopropyl, CH3, and then CH3. So you have to write the Fischer projection, and then only you have to identify what you call. Alright, so you have to write the names of these compounds. Let's write the names of these compounds, IUPAC nomenclature, right? 1, 2, 3. I'm going to write this as what? CH2, CH3. CH2, CS. Instead of writing it as what you call C2H5, I'm going to write it as what? Because you are writing the IUPAC nomenclature, maybe you have to choose the longest chain as the parent chain, isn't it? Right? So for which I am elaborating the names. You can see 3, 4, and then 5. 4 and then 5. Alright, so you can see you are going to number it from here as per the lowest locant rule. 1, this is 2, alright. Then 3 and 4, 3 and 4, 1 and the same, there is no difference. So number it, alright. You are going to write this ethyl as what? CH2 and then CH3. Number it. You have 1, 2, 3, 4 and then 5. Don't get confused, right? So you have the longest chain to be written here, which has most number of substituents or functional groups. CH2, CH3. You have a choice of picking up the right number 1, 2, 3 1, 2, 3. So you can see this side has more number of substituent. Then you have CH2, CH3. So whichever side you go, it doesn't make any difference. Both are same. So these are the compound that you got, right? Write the names of each compound. Then I'm going to write the name of this compound here. You can see this is 2. All right. There is a substitution at 2, 3, 3, isn't it? 2, 3, 3 trimethyl. Total number of carbon atoms are 5, so it has the pentanol group, isn't it? So the OH group is at second position. All right. So you can number this. You can name this compound also. Like you can see that this compound is 3-ethyl 2-pentanol. Is there any substitution? Yes, there is a substitution at 3-ethyl 2-methyl. Alright, let's write the name of this compound as well. You can see this compound is 1,1 dimethyl, isn't it? Then 2 has, alright, you can see 1,1 dimethyl. 2 has ethyl group CH2 CH3, 2 ethyl 1 butanol. Got the name, isn't it? Now we can see the name of this compound which I am writing. You can see that the compound is third position as ethyl, alright, and second position as methyl, alright. You can see the numbering. So it has 2 methyl. You can see the substitution, right? And then you have 3 ethyl and 3 total number of carbon atoms are 5, right? Pentanol. Alright, so you have to match it. Alright, you have to match it, isn't it? You are going to match it with the proper name of the compound, right? So whichever two compounds are having the same name are the identical compounds. You can see that Q and R are having the same name, hence they are same compounds, isn't it, right? So this is actually 2-ethyl, okay? So the compound is actually what? 2-ethyl, okay? So this is 2-methyl, 3-ethyl, isn't it? So the same compound, this is 3-pentanol. So name of the compound matters, right? So here you have to solve this question like this. Then look at the next one. You are treating this with a strong base, so dehydrohalogenation would take place to give you, but it must be mentioned that heating condition will only give you elimination product. And here also the heating is removing the hydrogen from here, giving rise to cyclopentadienyl anion, isn't it? Over here you have taken excess and you are using high temperature and presence of light. You know that you are going to get the addition product where all the chlorine units or molecules will be added onto the double bond. And over here when I are using what? Alcoholic KOH, 1 mole of HBr is lost. And when you are using NaNH2, that means what? Initially you will be getting what? CH3, CBr, double bond CH2. Then in the next step, when you are using a stronger base NaNH2, the HBr goes and you will be getting CH3, C triple bond CH. And you know how to write the product pertaining to this, right? I have told you already that if you are given any such question, you must solve it like this. You can see here that these are the starting compounds. So what is the product which is obtained? 135 trimethyl 135 trimethyl benzene is nothing but mesitylene, isn't it? So organic compounds, how many of the correct options are giving rise to the aromatic? You can see this has 4 pi electrons and cyclic delocalization, and it is anti-aromatic. This has total 6 pi electrons and cyclic delocalization. This is also aromatic. This is non-aromatic. There are no pi electrons at all. And you can see this compound is also having 6 pi electrons and cyclic delocalization. Therefore, this is also aromatic. So, how many compounds are giving rise to aromatic substances? Option B as well as option D. So, right answer for this question option B and D. Hope you are following, isn't it? The previous beautiful question here, you can see that the link between the structural and stereo is many times established in the JEE examination, and that link is beautifully crafted in this. You can see that there is a cyclic ether which we can write with that molecular formula, which has 1 degree of unsaturation, isn't it? So you can write the oxygen inserted inside the ring of the 5-membered, right? So you can see that the compound is having a plane of symmetry, so this doesn't have any stereoisomer, isn't it? Now we can write the 4-membered ring by putting a substitution. That substitution you can place it over here or you can place it at the other side, isn't it? So 1 or 2 is the position. However, if you see this unit, you can see that this is having the plane of symmetry, therefore this is a chiral. Alright, so I am writing here the optical isomers also. This is also a chiral because this has the plane of symmetry. However, you can see this serves as a chiral center, therefore you are getting here this one plus enantiomers because this is chiral. That means totally we got so far 1 plus 2 plus 1. That is, in this row you have got the total number of isomers that are possible is 1, 1, 2, and this has 2 units, right? So now you can move on to the 3-membered rings. In 3-membered ring you have the 2 carbon atoms and 2 in the side chain, right? So you can see that this does not have any plane of symmetry, therefore this is chiral, and indeed this is a symmetric center, therefore you will be getting one enantiomer of this. Alright, so in 3-membered ring, this is the last ring that is possible, isn't it? Now we can take methyl substitution in a trans as well as cis manner. Isn't it? And over there you can find that this compound is having the plane of symmetry, therefore this is a chiral. However, this does not have any plane of symmetry, therefore you will be getting the enantiomer of this. Alright, so totally 2 plus 1 3, right, plus 2 5. Okay, so we have this thing that this compound has plane of symmetry, right, you know, because we cut it like that. But please understand that this is also the chiral substance. Why so? Now you can see, imagine the molecule like this, right? You know, I have placed the molecule like this, which is having the carbon-carbon linkage over here and carbon-oxygen linkage here, isn't it? Now you can see the 2 methyls are lying like this. Now when you are cutting it, this portion is not along the plane of the molecule, isn't it? This portion is not along the plane of the molecule. You can see the 2 methyls are lying, whether they are lying at the same side or opposite side, it's a disymmetric part. That's called disymmetric part, isn't it? So don't think that this is plane of symmetry. As long as there is a foreign element in the ring, that will not be considered as plane of symmetry. This is what I found in majority of the students considering this as the plane of symmetry. You can see that the plane along which I am cutting or bisecting the molecule is actually this, which itself is unsymmetrical because of the presence of the oxygen atom in a 3-membered ring. However, that condition is not valid over here because this is the ring with even number of carbon atoms. So don't get confused between these two. Remember that if there are odd number of carbon atoms and even there are the identical group substitutions, that will not contain any plane of symmetry. So don't rule it out like this. So this also has the enantiomer. So total number of optical isomers that are possible are 10 but not 9. Many students, my own students, have marked the answer as 9 and K. Alright, so please be careful while solving such type of questions. Next question is straight. Like you can see, the Fisher presentation of D-glucose is given. Like we all know that, right? You know, D-glucose is based on usually this configuration. It's matching with the D-glyceraldehyde, isn't it? Now you have been asked to find out the beta L glucopyranose, that means 6-membered ring structures, right? Haworth projection formula, 6-membered ring structures. For description, I had given you some of the structures. I want you to go through all these structures. You can see beta D plus glucose, alpha D plus glucose, all the Haworth projection formulae I have given. According to that, you can see the beta, what is asked, beta L glucopyranose, right? You can see that beta L glucopyranose is the structure which is matching with the option D. So I want you to go through all the structure. There is no technique as such to remember them. You better remember the structures. You can see so let's see the next question, which is also based on the optical isomerism. So whenever you ask the question related to the optical isomerism, usually go for the asymmetric center. However, you should also follow the condition which are mentioned in the question. You can see that you are given a compound and you have been asked to find out the total number of optically active stereoisomers. And we usually adopt this formula if the compound is unsymmetrical. Like you can see the geometry of or configuration of this is not symmetrical. It is unsymmetrical, so we can follow this formula to find out the number of optical isomers, isn't it? However, there is a condition, this type of group, that means whichever are thicked portion, you can see that these carbon atoms geometry is fixed, isn't it? You can see the double bond geometry is fixed. So you can see the double bond geometry is talking about this. Double bond geometry is fixed. However, this one, this wavery thing, that is the hash line, is what you call variable, is not fixed. Then in that case, you see, when certain things are fixed, he is talking about only the double bond position, right? He is talking about this one is fixed. So I am not going to look at it at all. I want to consider the three positions, three asymmetric centers which can be varied. So these three positions will lead to what you call the optical isomers. That's it. Therefore, total number of optical isomers possible are 8. So these are the optical isomers that are possible. I'm not drawing, I'm not getting into it because it will take a lot of your time. You should have the shortcuts also. So we are not touching this because the double bond, you can see the question clearly says the double bond is fixed. It doesn't mean that thick lines are fixed. This can be varied. However, this is the chiral center as well. So you can see that I have identified 3 chiral centers, of which total number of optical isomers that are possible are how many? 8, but you can check one of its isomer when I am drawing it. You can make out from that. I am fixing this up. I am taking this towards the observer, keeping the double bond, isn't it? Keeping the double bond and writing the remaining, isn't it? Now we can see the upper is OH, lower is also OH, then the remaining group. Now you can see this compound has absolute plane of symmetry. So this is the meso form. So among 8, 1 is meso, therefore total number of optically active isomers are 7. Easiest solution possible, which is available on the internet. Let's see the question which is repeatedly asked in JEE about guanidine. In case of guanidine, what will happen when it accepts a proton, when it is accepting the H+. You can see the conjugate acid which is formed. The conjugate acid which is formed from the base is this, which is stable because of the 3+M effect of the identical NH2 groups. Now you can see that 3NH2 has the lone pairs and 3+M effect are going to stabilize this conjugate acid a lot. This is very stable. Therefore, this always comes first, right? Fourth always comes first. So you can rule out option D as well as option A. Guanidine is one of the most basic organic bases, isn't it? Then comes the next one. You can see the next one is this, because here also when you are writing the conjugate acid, it is stabilized by 2+M effects and inductive effect as well. So next comes is the compound 1 based on the stability of the conjugate acid. You can see anyways you got the answer, isn't it? 4 greater than 1 is this option, not even this, and then 2 and then 3. Between 2 and 3 you just check that this lone pair is freely available and this lone pair is involved in the delocalization. isn't it? However, this you can see is fully involved in the delocalization, so that this whole group becomes aromatic. So you might be having a question about the basic strength of this nitrogen versus this nitrogen. You can see that over here there is more degree of unsaturation. There is more degree of unsaturation. And you know that if the degree of unsaturation is more, then basic strength is less. So that's the reason why 3 comes in the last position. Very important, isn't it? The next question is little bit simple. You know that this is because of the pi electron repulsion will acquire the tub shape, isn't it? It will not be coplanar. Therefore, there is no cyclic delocalization of the electron. Therefore, this compound is regarded as what? Non-aromatic. Though it has 4 pi bonds or 8 pi electrons, it is not aromatic, isn't it? Right? So, this is not aromatic. This has 4 pi electrons, 2 and 2, cyclic delocalization. This is anti-aromatic. You can see that this has 2 pi electrons and cyclic delocalization. Therefore, this is aromatic species. You can see so far you found one aromatic species and there is no resonance here, not aromatic. And this has 6 pi electrons. You can see 3 pi bonds involved in delocalization, cyclic delocalization. Tropylium ion. What is the name of this compound? Tropylium ion. Aromatic. Now you can see this has 4 pi electrons, cyclic delocalization, anti-aromatic. Cyclopentadienyl anion, 6 pi electron, cyclic delocalization, aromatic. You can see benzene, irrespective of this, cyclic delocalization is there for 6 pi electrons, aromatic. Over here this is called phenanthrene, isn't it? Not anthracene. Phenanthrene, it has got a 3 plus 2, 5 plus 2, 7 pi bonds, that is 14 pi electrons involved in cyclic delocalization, that is 4 in plus 2, 4 into 3 plus 2, cyclic delocalization, 14 electron system is aromatic. So on the whole we have 1, 2, alright, 3, 4, what else? 5. Okay, so total number of aromatic species over here are 5. 1, 2, 3, 4 and then 5. Yes, the right answer for this question is 5, isn't it? Now let's see the question based on the reaction sequence. Alright, let's see what happens here. We've got a compound P which has got an ester group. You know your favorite reaction, COO, C2H5. You know when you are treating this with excess of methyl magnesium bromide, what's going to happen? CS3 MgBr, the popular nucleophilic substitution reaction where your OET is replaced, esters undergo the nucleophilic substitution, not addition. You have tertiary butyl, C double bond of CH3. This is not the product, right? Because you have taken excess of CH3 MgBr. When you have taken excess of CH3 MgBr, what will happen? Another mole will add over here, gives rise to a 3 degree alcohol. You know that when esters react with Grignard reagent in excess, they gives rise to what? 3 degree alcohol. So this is your Q. First nucleophilic substitution, then nucleophilic addition. So this is your Q. Now you can see this Q is heated with, isn't it, concentrated H2SO4. You have taken here H2SO4 and heating it. You know that dehydration will take place, alright, to give you a cyclic compound, arenes. You get a 5-membered ring, alright. So this is your R. Alright. Now R when treated with what is happening here? R when treated with CS3COCl. You can see that R when treated with CS3COCl CH3 COCl. Am I missing something? No, isn't it? You know, electrophilic substitution in presence of AlCl3 in dichloromethane is a solvent, followed by treatment with H2O produces S. ET in compound B is ethyl group. Okay, that's okay. So you can see this is activating group, right? Because it has two hydrogens. So this is the position which is vacant to be attacked, isn't it? Now, so when this is heated, I'm going to get this group and then COCH3 here. So this is the compound S. So what's the question? The compound, the product S is, where is it? Yeah, option A is the right answer for the question. What do you say, man? Okay. Yes. Then what do you have? Is that okay? Now you see the next question. Okay, next question is what? Q to R and R to S. The reactions have been asked. U to R and R to S. You can see R to S is a Friedel-Crafts reaction. That is acylation. And Q to R is nothing but dehydration. Or this is also electrophilic substitution only. So let's see the options. Okay. R to S is Friedel-Crafts reaction, isn't it? R to S is Friedel-Crafts reaction, alright. R to S is Friedel-Crafts acylation, dehydration and Friedel-Crafts acylation, isn't it? So right answer for this question number 36 is option A, right? So hope you understood the classes, isn't it? You can see, right, Q to R is the dehydration process and R to S is acylation process. Alright, so hope you understood the sessions. What do you say? Okay, so if you are liking the videos, please like, share and subscribe to your friends, relatives or the serious aspirants so that these classes are helpful. In the next session, we are going to see the hydrocarbon and onwards. So those sessions are going to be very, very important. So stay tuned. That's it for today.